like all of the cumulative sums that we've worked on, this one has a storyline and a picture associated to it, which involves dividing things up. If you have a roadway, if you like, and you have mileage markers along the road, like this, all the way up to, say, SN here, then the length along the road is this, described by this parameter S, which is arc length. And if we look at a graph of this sort of thing, if this is the last point B and this is the first point A, then you can think in terms of having points above x1, x2, x3, etc. All right? The same as we did with Riemann's sums. And then the way that we're going to approximate this is by taking the straight lines between each of these points. Now, as things get smaller and smaller, the straight line is going to be fairly close to the curve, and that's the main idea. So let me just depict one little chunk of this, which is like this, one straight line, and here's the curved surface there, and the distance along the curved surface is what I'm calling delta S, the change in the length between, so this would be S2 minus S1 if I depicted that one. So this would be delta S is, say, SI minus SI minus 1, some increment there. And then I can figure out what the length of the orange segment is, because the horizontal distance is delta x and the vertical distance is delta y. And so the formula is that the hypotenuse is delta x squared plus delta y squared, square root. All right? And delta s is approximately that, so what we're saying is that delta s squared is approximately this. All right? So this is the hypotenuse squared, and it's very close to the length of the curve. And the whole idea of calculus is that in the infinitesimal, this is exactly correct. All right, so that's what's going to happen in the limit.